Good morning, all of you. Dear students, kindly maintain the decorum in the online class. So today we are going to discuss the topic on multi-layer perceptron. Okay. So already, so the entire agenda, the today class, we are going to have some little overview of the single-layer perceptron and why do you want to learn the multi-layer perceptron, what is the necessity of that, and how do we build the model on the multi-layer perceptron. And also, as already we know that every concept we have to associate it with some numerical problem. So this also we are going to apply some numerical problem on the multi-layer perceptron, and finally we have to conclude on some application. And before getting into this multi-layer perceptron, already you had a discussion about the single layer perceptron in the last online class. So I'll give you the overview of single layer perceptron. Say for example, how the single layer perceptron will be. In the name itself, we do have only input layer as well as output layer, right? So the input layer, we have n number of neurons. It is starting from x1, x2, x3 till xn, and also the associated weight W1 to Wn, and the processor unit. Here you have to apply the activation function and the other weighted sum. Finally, you will get an output. So it is having only the input unit as well as output unit. That is input layer and output layer. Say for example, here, if you want to recognize the pattern, okay, so generally the neural network, here we are using one example for pattern recognition. I want to recognize the pattern. Okay, so I want to recognize the pattern 8. Okay, so what will happen? The 8, it will take the pixel value. So the pixel value in the sense 28 into 28 pixels, so 784 pixels. So that pixel value is given to all your input neuron. So all these pixel value is given to your input neuron. Now the associated weight value is also given. Okay, so along with this associated weight value and that input pixel value, it is given to your processor unit. So in the processor unit, what will happen? It will perform the summing up all your input and the associated weight value, and you are applying the activation function along with that. Okay. So once you apply the activation function with the weighted sum, it will produce the output. So this will produce an output. Here, the output will be 00010. Excuse me. So now we are getting the output value. So the weighted sum. So that is your output value. So this output value will compare with all these probability. So which probability is matching? Say for example, if you recognize the pattern of 8, so if it is matching the 8th pattern properly, then automatically your actual output is equal to your desired output. Then there is no need of weight updation, right? So in case if your actual output is not equal to your desired output, say for example, if you want to recognize the pattern 8, instead your neural network is recognizing 2 or 3 or like that. Okay, so what will happen? Your actual output is not equal to your original output. So what we have to do, you have to modify this weight value. Okay, so modify, so you will get some error. What is the error? Your actual output is not equal to your desired output. That is called as an error. So to reduce the error, you have to update your weight here. So update your weight in the sense you have to modify the weight until your actual output is equal to your desired output. Okay, until your system recognizes that your input pattern is 8, then that is called as the correct output. Until then, you have to update your weight value. So this is the process behind your single layer perceptron that you already had in the previous online session. So here the people might think that what is meant by weight value, why you are saying this weight value, how it is differentiated from your normal neural net, that is the BNN as well as ANN. BNN in the sense biological neural network, and ANN is nothing but artificial neural network. Say for example, if you want to identify a particular person, so what we have to do, that particular person features are nothing but as an input. Yes or no? They are as an input. And the weight value is nothing but the associated information which will help to identify your output. That is called as a weight value. Say for example, if you want to identify a person, okay, so the person name, maybe his color, or where you met the person earlier, like that. So there's some supportive information which will help to identify the pattern, that is called as a weight value. That is called as a supporting information. When you use in the BNN, biological neural network, we will say like that. The same simulation we are making into the artificial neural network. So the supporting information which will require to identify your pattern, that is called as a weight value. Hope you understood what is the meaning of weight value in your artificial neural network. Correct. So this is the way. So I'm summarizing this for a single layer perceptron. So in the single layer perceptron, what we have to do? The single layer perceptron, you have to take the input pixels of all your pattern in your input unit. And now that input unit is associated with some random value of your weight value, and that is given in your processor unit. So that processor unit will do the summing up function. And after the summing up of all your input and the associated weight value, it will apply the activation function. So the activation function in your single layer perceptron is a step function. Okay, f of x is equal to x. You already know that. So that activation function you have to apply over the weighted sum, you will get an output. Once you got the output, you will compare your actual output and your target output. Okay, so if the output are same, then there is no error at all. Okay, if the output are not same or it is incorrect, what will happen? Again, that error value you want to reduce it. So how do we reduce the error? You just modify this weight value. Okay, and again, if you modify the weight value, and you have to repeat the same process again and again until you got the desired output, final output. So this is the working principle of your single layer perceptron. Might you already discuss about the algorithm numerical problem earlier in your previous class. Now we are move on to the next. Today's session is called as a multi-layer perceptron. So in the multi-layer perceptron, why we want to go for the multi-layer perceptron? Why we can't able to solve certain problem in single layer perceptron? What kind of problem we cannot able to solve the single layer perceptron? So that is what we are planning to discuss, the multi-layer perceptron now. Okay. So in the multi-layer perceptron, especially it is used for linearly inseparable problem. What is linearly inseparable? And before that, we should know what is linearly separable problem. What is linearly separable problem? Say for example, take a AND operation. So in the AND operation, what we have done? Yeah. So in the AND operation, here we do have, look at the truth table. In the truth table, we have two combination, true, false and true, false. So if it is both are true, then it is true, and the remaining all thing is false. So by using a single linear classifier, we can able to classify these two samples. That means the true is positive sample and false is a negative sample. So by using a single linear classifier, you can able to classify your positive sample and the negative sample. That means easily classify the class A and class B. So this AND operation is a linearly separable problem. And similar way, take one more example, is called as a OR operation. So in this OR operation also, look at the truth table. If both the combinations are false, then only your option is also false. Yes or no? Here also you can easily classify the class A as well as class B, because all true are positive sample and F is a negative sample. So by using a single line linear classifier, you can easily classify the positive sample and the negative sample, since we are calling this also a linearly separable problem. Now, come to our topic, right? So linearly inseparable problem. What is linearly inseparable problem? Right? So say you have to take an example of XOR operation. So in this XOR operation, look at the truth table. If both that means it is OR, not a AND. That is a meaning is called as a XOR, right? So if both the values are true, then it is false, and both the values are false, then it is also false. So the remaining combination is true. Look here, for this kind of data samples, you cannot able to classify with a single linear classifier, right? So that is what we required. You can have more than one classifier here. Based on that, you can classify your samples, positive and negative sample. That is what this XOR type of problem is called as a linearly inseparable problem. So the linearly separable problem, your AND operation as well as OR operation, you can use it by using a single layer perceptron. You can solve this problem, but in this XOR, by using a single layer perceptron, you cannot able to solve this kind of linearly inseparable problem. That is what we said. Your multi-layer perceptron, it is going to solve the linearly inseparable problem. So how we are going to solve that things we will discuss now. So say here, how do you are going to develop a model on your multi-layer perceptron? Look here, we are taking the input neuron. Okay, so this input neuron, again it is a combination of the switches. In the switches we have the two options, true, false, false, true, like that. Okay, so this switches is given as an input to your the next layer. The next layer is called as a 1. So this will produce your AND operation. Okay, so this will produce your and this will produce your OR. Right. So by using this input, we are getting by developing a single layer perceptron, you are getting the output of your AND operation. By using this single layer perceptron, we are getting the output of your OR operation. Now, so that is what we are given this representation also for the truth table representation for and truth table representation classification of your OR. Okay? So now by using a single layer, single linear classifier, you can classify this data sample, and similar way, this data sample also we can use a single layer, one linear classifier. Now combine these two output of 1, output of 2 neuron, you can combine the third neuron. It is going to solve the linearly inseparable problem or XOR. That means the output of OR as well as the output of not an AND is going to produce your the final layer that is going to produce the output of your, that is going to solve the problem of XOR. You understood? So this is taking from not and this is taking from OR operator. Now you can able to classify the linearly inseparable problem. Right? So for this only, look here how many layers we have used, more than one layer. So this is your input layer, this is your hidden layer, we are going to call it as, and this is your output layer, that is your third layer. You got it? That is what, if your model is having more than one layer, then you can call it as it is multi-layer perceptron, right? Now you've seen all these example. Okay, so how we are, what is the need of multi-layer perceptron? Why we need the multi-layer perceptron? For solving the linearly inseparable problem only, we are going to have the multi-layer perceptron. So it is a combinations of more than one single layer, which will produce one more hidden layer that is called as a multi-layer perceptron model. So look how the model of your multi-layer perceptron will be. Listen, so here the first layer is called as an input layer. Okay, so the n number of input will be there. Here the sample we given the 3 input switches we given, 3 input neuron, and we have one more layer is called as a hidden layer, and another, the last layer is called as an output layer. You can have more than one hidden layer also. In similar way, you can have one output unit as well as more than one output neuron also. Okay, so what will happen? You have to give the feed the input to the input neuron, and now the input neuron will associate some weight value, and that weight value, associated weight value, and the activation function, apply the activation function, and it is given to the hidden layer. Now the hidden layer also will have some weight value, and that will be given to your, and again it will apply the activation function, again it will produce some output. That output will be the input of your final output neuron. Now the output neuron will take a outputs. Okay, so how the model will work? So the input layer will take the associated weight value and apply the activation function also, and that output will be given to the input of your hidden layer. So now you will be getting some output in your hidden layer also. So the output of the hidden layer will be the input of your last layer. Yes or no? Now you will be getting some output here. In this output layer, you will be getting some output here. What will happen? Now again the same process. You compare your actual output and your desired output. Okay. So if both the outputs are same, then there is no need of weight modification. In case if both the weights are not equal, if both the output are not equal, your actual output is not equal to desired output, then what will you do? You have to feed forward that error value back to your hidden layer. Okay, that error value is given to the hidden layer. Now the hidden layer weight value will be modified. Again, in turn, you are modify the weight value of your input layer also. So you repeat the process. Again, you repeat the same process until your actual value is equal to your original value. Actual value equal to your desired output. You understood? So this is the working principle is same as that of your single layer perceptron, but here we do have a back propagation learning rule. We are going to use it. So once you go to the next problem, you can easily understand. See, in the coming to the threshold function. So in the threshold function, in the multi-layer perceptron, we are going to use the sigmoidal threshold function. Hope you already know the threshold function, which you used in a single layer perceptron. In the single layer perceptron, you use the threshold function as a linear threshold function. That means your f of x is equal to x. That is your linear step function you already discussed in the single layer perceptron. So this threshold function you already use it. Now for our multi-layer perceptron, we are going to use a sigmoidal threshold. For a smooth learning, we are going to use the sigmoidal threshold. That is the activation function we are going to apply on your net weight. Okay, so the net weight in the sense input, then the associated weight, that is called as your net weight, is equal to 1 by 1 plus e power of minus k net. Okay, so the k net in the sense it is a k is a small random value that will be along with your net weight value of your the entire network. Okay, so this, remember this formula for your threshold function, 1 by 1 plus e power of minus k net. While we are solving the problem also, we are going to use this threshold function. Okay, so remember clearly, if you are using a single layer perceptron, you have to use the threshold function as step function. F of x is equal to x. And if you are using the multi-layer perceptron, you have to use the sigmoidal function, that is your threshold function. So the formula for your threshold function is 1 by 1 plus e power of minus k net, right? And here the learning rule what we are going to use it is called as a back propagation rule. What is meant by back propagation rule? I already told, look here. So back propagation rule is, see, finally, we are got some output. Yes or no? Say some pattern recognition or something, right? Or medical diagnosis for any kind of application. You got some output for an initial iteration. You got with your original output.